Welcome everyone. Today we're diving into the fascinating realm of diffusion through a solid, a fundamental concept in chemical engineering. But don't worry, we're going to make it fun and accessible and easy to understand.
So, what is diffusion? Diffusion is simply the movement of molecules from an area of high concentration towards an area of low concentration. This is shown in the photo as the molecules go from being bunched up in the corner to spreading out throughout the fluid. Today we'll be demonstrating diffusion using items that you can find at home. There are only a couple items needed to conduct this experiment. You will need a white potato, a sweet potato, a knife, food coloring, a ruler, and a cutting board.
Now, we'll go through the step-by-step process of conducting our diffusion experiment. Once you have all your materials set up, we can begin. For slice preparation, carefully cut thin, cross-sectional slices from both the potato and sweet potato. Lay out the slices side by side on a clean surface. Set up your camera with a clear view, pat the potato slices dry with a paper towel, as shown here. Now carefully add 1 drop of food color onto the center of each potato slice. This is our starting point for observing the diffusion process, so be as precise as possible. Start the timer for 1 hour and leave the slices in a location where they won't be disturbed throughout the experiment. We will review experimental results in the next section, but please ensure you periodically return to observe and document the diffusion process. After 1 hour, stop the timer and photograph the final result.
Here is a time-lapse of the diffusion of food dye through the cross-sections of the potatoes. For the regular potato, diffusion was not uniform in the radial direction, which made the diffusion difficult to measure. About 15 minutes after the first drop, the food dye began moving in a straight line toward the edge. We notice pooling of the food dye in the regular potato due to lack of even diffusion. The food dye moved more uniformly in the radial direction for the sweet potato. We estimated the line of food dye to be about 3 centimeters in the regular potato. We roughly estimated the final shape of the food dye in the sweet potato to be a circle with about 2 centimeters of food dye in any direction radially. We hypothesized that the content of each potato may influence the diffusion. The sweet potato has 1.3 times more fiber and 2.7 times less starch than the regular potato. We also know 3 facts. The food dye is water-based, fiber is soluble in water, starch is insoluble in water. Given these facts, we reasoned that the higher fiber content and lower starch content in the sweet potato may have contributed to more even diffusion in the radial direction.
We understand these effects on diffusion through the relation to the terms in Fick's first law, which governs the diffusion flux. For example, we know that the sweet potato is less dense than the white potato. As a result, the dye diffused faster through the sweet potato because diffusion flux is proportional to system density. Additionally, we can model this equation only in the radial direction because we sliced our potatoes thin enough that the z and theta directions are negligible. Fick's law guides our understanding of the system and how we can learn from this experiment. So what do colorful potatoes have to do with chemical engineering? Understanding diffusion through solid is crucial in labs using analysis techniques like TLC plates. This concept helps researchers measure and analyze results in chemical research by separating and identifying components using diffusion of the liquid substances through the solid plate. Other real-world examples of diffusion through a solid include solid-state alloying, drug delivery systems like drug patches, making pasta, and marinating meats. We're very dedicated to these culinary applications.
So when we were doing this experiment in the kitchen, we made a few mistakes because we're only human. But no worries, we've got some ideas to make things more accurate next time. First off, when we were adding food dye to the potatoes, we kind of just dropped it on there. Turns out, depending on how hard we squeezed the dye bottle, different amounts came out. To fix this, we can use a pipette to measure the dye more precisely. That way, we know exactly how much is going onto each potato and it would be easy to measure mass and volume. Then there's the issue with the potato thickness. Cutting them evenly was tricky, and with the white potato, one side ended up thinner than the other. This made the diffusion happen in a line instead of spreading out. To avoid this, we could use a potato slicer to make sure they're all the same thickness. That should give us more reliable results. So with these changes, we're hoping our next experiment will be spot on. So there you have it, the science behind diffusion through a solid right in your kitchen. Who knew chemical engineering could be this exciting? Keep exploring, keep experimenting, and who knows, you might be the future of chemical engineering. Thanks for joining us on this scientific adventure.